Hi, my name is Daniel Anolik, a solutions architect for Jeppesen, a Boeing company. Jeppesen creates aviation safety applications and data for pilots and flight planning personnel all around the world. Our data is cyclical in nature, is updated frequently, and terabytes of that data must be distributed to hundreds of thousands of pilots all around the world. In this next presentation, I'm going to explain how we use Perforce to help manage our data and the state of that data in the cloud for distribution. It's great to be here at the Merge conference. I've worn many hats in my career, and one of the hats that I keep weaving in and out of has something to do with SCM. Why I keep coming back to that, I seem to have some sick passion for organizing chaos. And there's plenty of problems to solve in that SCM world, and I like putting organization around that. And like this mantra says over here, I believe strongly in versioning everything. And so that neuroticism around versioning everything led Jeppesen to building a data distribution system that allows us to version our aviation data and the state of that data in the cloud. And in the next half hour, I'll give an overview of that system and how we used Perforce at the heart of that system to help manage our data. In the personal realm, I've been a search and rescue volunteer and a wilderness navigation nut for many years. And that is a lot of what led me to Jeppesen in the first place, somewhere where I can work with maps and charts and routing and navigation things for a living and do software. Was a great fit. And I'm also a very happy parent of this cute little girl. Come on. Yeah. Yes. What do I do these days? That. So Jeppesen's an 80-year-old company. We build software for all aspects of the aviation industry. The start of Jeppesen was around safety charts for air travel. The founder, L. Ray Jeppesen, was flying in and out of Denver over the Rockies, a very dangerous place to fly, and he would take notes and he would make charts, originally for his own safety, then for his friend's safety, and eventually that was a business, and eventually there was charts everywhere, and pilots all over the country and all over the world were flying with Jeppesen charts for safety. Fast forward some decades, and that's all digital data, and but the core goal has stayed the same. It's really about keeping air travel safe, safe for the pilots, safe for the travelers. And so we have a number of software products now that are airborne navigation apps that run in the cockpit, and ground-based planning for dispatchers around aviation safety. The image you see on the left is one of our flagship products these days. It's called a mobile flight deck, and it runs on a variety of tablet platforms. And this is used by a significant percentage of commercial pilots now to provide the latest chart data and en route data and planning information while they're flying. So if you see me later at the conference, odds are good I'll be walking around with a tablet in my backpack, and if you want to see it, you can. The applications themselves can be quite impressive, but the real core value at Jeppesen is in its data. There's an enormous amount of data that's aggregated from all over the world and analyzed for safety of flight, and it's getting that data out to the different applications to be used in different ways. That's the core of this system that I'll be talking about today. So massive data, charts, airplane schematics, approach, procedures, policies, you name it. They're going to mobile devices, they're going to in-cockpit systems, they're going to PCs. The data is updated frequently. Some of our data is cyclical on a monthly basis, some of it's on a weekly basis, some of it's daily, some of it is every couple minutes. And so we've got a lot of data to move. And some of that data is quite large. The challenge that we started with here was around distributing all this data, all this safety critical aviation data to many different kinds of applications running on many different platforms, supporting the frequency of the updates to it's literally hundreds of thousands of customers updating constantly. It's moving terabytes of data each month. And some of the data, as I mentioned, is quite large. And being that it's cyclical, it often comes online at and the requests to download it all come through at the same time. So you'll have a couple 100,000 people hitting for this multi-gigabyte data set all at once, right? So you can't be don't want to be a bottleneck for that. So the original architecture proposal that my team put together around this was to abstract out the publishing of that data from our data creation processes, and to abstract that out from all the applications that download our data. So we've got many different systems at Jeppesen that are producing different kinds of data. And that's all represented in the data production magic box up there, right? And so they don't need to know anything about how the data is getting to the clients. They just need to be able to publish it somewhere. So likewise, the downloading applications, the consumer applications, need to just have an efficient way of finding, locating, authorizing, and retrieving and accessing that data. So we designed this system initially to abstract out both ends of that. And some magic would happen in the middle, and data would end up in these great places in the cloud, and they would be geocached wherever they're needed and downloaded seamlessly by the clients. And so what we had envisioned internally in that black box was there'd be some sort of publishing interface, there'd be some sort of, we called it a data brokering interface. Data brokering is, hey, I'm flying in this region, I need this type of data for this type of coverage. What do you got? How do I find it, right? And then, so somewhere in that black box, there's a whole bunch of workflow magic, which involves packaging up the data, doing whatever transformation, doing whatever working of the data is needed to make it now easily available for clients. And so what the initial vision had, that data comes in, we put it over here on a file server, we kind of work with it, we stage it, we do these things, then we push it out to our geocache locations for download. Once we got into the details of that project, a couple of pesky implementation constraints came up, right? So we've got to control access at a fine-grained level. So we've got different systems publishing in different places, different people updating the metadata around those data sets. And so we want to be able to control who can access where, who can publish to what. That's the kind of thing you could still do on a boring file server. A little more painful than doing something with Perforce protections, but it could work. We needed atomic change sets for publishing files. This was one of the big ones, right? So atomic change sets with aviation data, you can imagine, you've seen how most mapping programs work. There's, if you're looking at different zoom levels in a map, there's different tiles, and as you go up or down, you load in those different tiles. You can imagine if we've got 1,000 tiles for an area, or 1,000 files that represent a data set, and you only get 950 of those, and somehow the other 50 just sort of didn't make it, or you're on old data, that's not a good thing for aircraft flying or landing, coming into an airport. You could be a pilot that has flown this route for the last 3 years, and every day you land in this airport on this runway, but today that runway is under construction, and you need to know that, right? And so this is all the data needs to be updated all the time, and it needs to be updated atomically. And so some sort of need to track atomic change sets through the entire workflow became a core requirement. Detailed history tracking, there's a lot of auditing that needs to happen in our world, FAA auditing, and both from our own quality perspective. We need to know who's publishing what at the time, what the state of any data was at any given time. If heaven forbid there was an accident, we need to be able to know exactly who had what data, when. So we need to be able to track a lot of history. Individual file restores is a very good thing. We might be publishing data, and we might be running it through some final tests in-house, and discovering that before that data leaves, it doesn't meet all the success criteria, and so we need to hold it back or roll back or compare. And so it really started to sound like we needed a formal content management system here. And so the next iteration looks a lot like the original architecture, but that boring file server is replaced with Perforce. So all of the data for our data distribution system now actually flows through Perforce. And I'm going to explain a bit about how we leverage some of the different Perforce features to make that happen. First of all, why we chose Perforce over other content management systems. It just happened to support all the implementation requirements that we had with very little customizations. The APIs are quite easy to work with. We've been using Perforce in-house for our source code management for years. That's gone very well. We continue to grow our user base around Perforce for source code management, so we had in-house expertise. It had been very reliable. It's one of the few things we haven't had to worry about too much, and so we felt comfortable with that. Also, efficient, scalable blob storage. I mentioned some of our data sets big. I didn't know that there was a contest for biggest files going into Perforce until earlier, but no, I don't want to steal Nuance's thunder, but we've got larger than 10 gigabyte data sets moving in there all the time, and quite a few of them. So that's one thing that we tested originally. For our source code management side, we had never done that, but we knew that that was coming down the pipe. We tested that in the beginning. Perforce is happy with ridiculously large files. So leveraging some of the key features in Perforce. So I mentioned how atomic change lists are one of the key things here, talking about moving an entire set of data through. And so we need to make sure that as data goes from the publication, the production side through our system and becomes available for clients, that nothing's available until it's all available, right? So hooray for Perforce atomic change lists. All the file sets are submitted in a single change list, and then we can track everything through that. We publish it to our cloud locations. I keep waving my hands when I say cloud locations. One of the reasons for that is we use multiple cloud locations. Part of the idea of this system was also to abstract out cloud vendor implementations. We didn't want vendor lock-in. So we're using a mix of our own data centers and a mix of third-party cloud storage providers. If you're not familiar with what that is, maybe you've heard of things like Amazon S3 or Google Storage or Microsoft Azure, Rackspace. Everyone's got it, right? It's a good thing. You have these. We like to call it the big hard drives in the sky, right? There's just this unlimited place you can put stuff, and then you can control your authentication. You do HTTPS authentication. We do time-based signatures and all kinds of other locking, and it all comes out very secure, very scalable. They're in all parts of the world that we're not, and that's great. But we didn't want vendor lock-in, so we want to be able to push out to those places. But cloud object stores, if you're familiar with those things that I just mentioned, you know that they don't think like Perforce does. They might offer versioning, but it's per file versioning. They have no concept of change sets. They have no concept of these files go together, or I need to roll back this entire set of files. There's no such thing as a label or snapshots, like a NetApp style snapshots in cloud object stores. So we wanted the coolness of the cloud object stores, but we wanted change sets. So we're tracking, so what we do is we track all the metadata on our own. We push things out to these object stores. We track all the files and the state of the files and make sure that they're all okay. And then, according to our baselines, we unload things and make them available. So files are never available until all the files of that given change list are available. So Perforce history tracking, as I mentioned before, helps us tell us what files were published, when, and by whom. Spec depots are awesome. If you're not using spec depots, use them. They don't cost anything extra with Perforce. They give you a lot of great audit ability. Soft deletes of files. So a Perforce delete allows us to actually remove files from what we consider our active lists. It allows us to remove them from various cloud storage locations without permanently purging them out of our depots. We do have data retention requirements, but what we retain live and what we retain sort of in a Perforce repository soft deleted are different. And so it's nice to have that ability. Our data typically goes through what we call the death cycle of data at Jeppesen. First it's expired, which means it's hidden. Then it's soft deleted, and then it's obliterated at some point. Counters are I think underrated with Perforce. Call me weird, but I really like Perforce counters. They're an easy way to keep track of state of certain things. So we use the counters to track. We've created custom counters for all of our different data types, and we use those to track the last known good change list of that data being processed. So this helps us do incremental updates. So if I've got 50,000 files in a given data set under a given depot path, and I just published 3, and I need to sort of process those. How am I going to track where was I, which files were already processed and which still need to be processed? You could look that up by scanning 50,000 files, or you could just look at a custom counter very quickly, very cheaply, and say, the last change list that made it through successfully was this. That's my last known good. Here I am. Ask Perforce a very quick query. What are the files that were different since that last change list? It's these 3 or it's these 300, and I'm going to work on those. And when I finish working on those, I'm going to update my counter. I'm going to rinse, repeat, right? So counters, good stuff. They're durable. They're as durable as the Perforce database too. So locks are another thing. So normally in our software development use of Perforce, we don't really do exclusive locks. It's a rare thing. People check out the same file, they work on it in parallel. The first one in wins, the second guy has to merge, right? And locks, though, were a way for us to help implement job queuing and workflow. So we're actually doing the publication and data processing queue management in this Perforce system as well, where when requests come in through our web services interfaces, those need to be stored in some stable way. We need durability on the requests. If any piece of the system crashes at any time, we need to not lose those requests, right? So a request comes in through a web services interface, a job file is created in Perforce, that when that atomic change list is successful, the service interface returns a success. I have your job request, it's now durable, right? And if Perforce crashes, which hasn't happened, knock on that, yet there is no, it can come back, those job requests exist, right? And so we use actually locking to process those. We might have n number of servers scaling horizontally, picking things off the queue, and how do they know what to pick off the queue? They take the latest one, they lock it. Next server knows not to touch the one that's locked. It goes to the next one that's not locked, and they're processed. So Perforce locks came in handy. Perforce branching came in handy as well. We actually use branches to track the promotion level of the data in this system. So by default, the data that comes through our system is staged into its final location. It's made available. It's all set up, ready to go, except for the metadata around it doesn't consider it released, doesn't consider it public. So our internal automated tests and manual tests have the ability to work with the data in its final resting location before it's actually publicly available, right? And so an easy way to implement that is it actually all goes into one depot path, and then to mark the state as promoted to public, we just do a Perforce integrate. So our automated processes, they pass the tests, they do a Perforce integrate. When it's picked up in its new depot path, the metadata around it is changed and acknowledged and is public. So the branching gives us a nice visual on, if you look at the history on a file, just like with your source code control, I see, it came in here, it did this is when it was branched from stage to public. Great. Security. So this is pretty standard that if you're creating a system with a lot of automation around it, that your service account should have access only to exactly what they need. So you don't want to create, so they can read only what they need to read, they can write only what they need to write. So a number of service accounts, Perforce protections is plenty flexible for that. We're using it to restrict access by depot path and pattern matching on certain file types, certain metadata file types, and also specifically IP addresses of machines that would be doing certain job processing for this. The Java API was used for 100% of the interaction between our custom development, our web services, and Perforce in this case. We found the API to be quite easy to work with. It's allowed us to do everything from reading and writing files, doing those P4 integrates for promotions, updating the counters, change lists, reading change list details, and also what we call expiring content. So expiring content, again, going back to that death cycle of the data, is updating the metadata around the files, and which is writing files in Perforce, doing deletes of the files, and eventually doing obliterates. So I think obliterates are actually maybe the one thing that's not happening through the API, because I don't think that's supported. And the result of all this is really what we were hoping for and more, because we now have this uber scalable object storage for distributing our data that does, where we have full configuration management of it. Again, we can see the state of our cloud resources at any time. We can release data based on those atomic change lists. We can roll back any part of our cloud. That sounds weird, but I can roll back any of those branches, any of those depot paths to any change lists in P4V, and the cascading effect is that our job management processes, it's very similar to thinking about a CI build or what happens with your continuous deployment around software. Is you check things into Perforce, something's watching a depot path, and something then, a series of events is triggered and acted on that, right? And so you might have a build happening, some packaging, some chef deploys, whatever. In this particular case, it's a lot of a similar mindset, just used very differently. So as things change in depot paths, we've got other job agents working on processing that data and adjusting the state of our cloud resources for it. So the ability to actually roll back and forth cloud resources has been, we've come up with more uses for that than, now that we have it, than I imagined we would when we built the system. The ability to roll back individual files, to troubleshoot, to see history on files has really been excellent. And the atomic change list management has also been very key. So someone had asked me recently, would you do this? What lessons have you learned from this? What would you do again differently? And I'm not just saying this because I'm standing at the Perforce conference, but using Perforce at the core of this system is something I would definitely do again. It's proved to be the easiest part of this system to work with. That's the part that works. And as I mentioned, we've come up with uses for Perforce that we really didn't think we're going to have in the first place. We've had in helping debug and troubleshoot other applications or other data issues. It's turned out that I can go back and I can look at these spec depots, or I can go back and look at this Perforce history, and I can come up with sort of different data and reporting that helps solve some other problem at some other part of my organization that we wouldn't have really had. Because if you've built applications before and had to look through their logs, there's some general rule around that is logs are great at telling you something that you already knew you needed to look for, right? So the first time a problem comes up in your app, if this is a new app, right? You think you go to look for what happened. It's not in the logs. Great. Okay, I'm going to add that to the logs, and you start adding more things to your logs, and eventually you have logs that tell you kind of everything you need to know. Well, when we first built this app, we really didn't know all the things we were going to need to know. It was just convenient that Perforce keeps track of everything. So that was very helpful. Some of the things that we would have done differently, or that we have done differently in newer iterations of this, is actually more around the other magic boxes. Like I mentioned, those counters. We didn't initially implement those counters. Our data sets weren't as large when we started using this. And so we would just process all the data all the time, and then the need for faster processing of incremental changes led us to the adoption of those counters. I'm going to prime this pump with some questions that were someone asked me earlier today. Someone else asked, what are the next steps that you're planning on as we evolve this? We have, so far, all of our data production has happened at our core site. I work out of a Portland, Oregon office, but our headquarters for Jeppesen is in Denver, Colorado, and all of our data production has been happening in Denver, and so all of the publishing has been happening from Denver. But something that's starting to happen now is different data types being produced in other sites and other places, and so how should we deal with that? Should we get everything to Denver and then get everything back out again? Or maybe we can just do a more distributed model. And so after a little bit of experimenting, it looks like federated Perforce servers are again coming in with an unexpected benefit in that I can use Perforce replication to transfer only what I need. I can transfer the metadata back and forth across all our sites and master that at our main site, but I can leave big blob data in its home locations and have my publishing agents directly work it from there. So that's another nice benefit of not having homegrown anything, of just using Perforce at the core here. Thank you.